In this video, we are going to look at the sample size required to estimate the population mean mu with a certain accuracy. So in other words, say this whatever the population with a mean mu and sigma, the standard deviation. So we want to estimate mu. So in other words, we are looking at the sample size you need to pull from the population to estimate mu with a certain accuracy. Say for example, you want to estimate mu with a 100 times 1 minus alpha % confidence interval. So with the error plus or minus error E. So in other words, that's the margin of error we are looking at. In different words, like say for example, when you ended up with a confidence interval, so your interval goes like that: x bar, z, sigma, z table values, sigma over square root of n, plus or minus that part. So this is the part we say that the margin of error, this part, okay, plus or minus. So it's centered around the x bar, the average, and the minus and the plus. So you can see that. So this plus or minus part, in other words, this part, when n is getting bigger and bigger, that this is going to be getting smaller and smaller. So in other words, your confidence interval is going to shrink if the sample size is getting bigger and bigger. So in other words, by increasing the sample size, always you can achieve the accuracy you want. So that's what we are trying to see. So in other words, you know the accuracy you are looking at in advance. If that's the accuracy you are looking at, that accuracy, then by increasing the sample size, you can achieve that goal. Okay. So the length of that interval, which is this value minus this value, which is going to be 2 times, so the x bar will cancel out, 2 times the length of this piece, that is going to be, so that should be same as the 2 times e, the plus or minus error part, okay, 2 times c. So that got to be the this got to be same as that, so the 2 will cancel out. So if you put the square root n onto this side and the e down here, so the square root of n should be equal to z table value times sigma divided by e. All right, so the n value, if you take the square, n, that quantity is square. So this is the formula. So in this formula, so the first note, for you to use this formula, so of course you need to know the sigma value, otherwise you cannot use it. Okay, so sigma must be known for you to use that formula. So in other words, you need to have, if you do not know the sigma value, at least you need to have some kind of rough estimate for that sigma. In other words, a prior estimate. See, when you do things most of the time, you know something about that thing based on your prior knowledge. You need to have some kind of prior estimate for that. Okay, at least some kind of rough idea of what is going on. Okay, so that's, you need to have those two values, because you are trying to do this thing before you pull your random sample. So that way you don't have a estimate for that. Okay, so you're looking at how big sample you want to achieve a certain accuracy. All right, so that is that note number 1. The second one, when you evaluate this thing, okay, so when you evaluate this thing, so if you get a decimal number, so usually, see this is supposed to be an integer. You kind of round it down to get the integer. But in this case, you need to round it up, okay, rather than round it down. So the reason is that, see, you are trying to achieve your goal. So to achieve that goal, if you round it down, you're not going to achieve your goal. So you're going to might be missing by a little bit. Okay, so you need to round it up. So the third one, initial populations must be normal unless you're looking at a large n value. Once you figure it out, unless this n is large, this initial population kind of has to be normal. See, after all, we got this interval by assuming that, so either this got to be a normal curve or n has to be large, so that with the central limit theorem we got that nice curve. That nice curve gave you this interval. All right. So in other words, so when you figure out this, if n is small, then basically that the assumption this has to be a normal. Otherwise, that n got to be large. Okay. So in general, the thing is that assumption is that this has to be a normal curve. But if you end up with a very large n, then you can relax it anyway. Okay. So that's what it is. All right. So let us look at an example. So in this example, so please read this one. So here you want to estimate a cup of coffee contain an average of 115 milligrams of caffeine with an amount per cup ranging from 60 to 180 milligram. All right. Suppose you want to repeat the FDA experiment in order to obtain an estimate of the mean caffeine content in a cup of coffee correct to within 5 milligrams with 95% confidence. So in other words, at the end you want to estimate mu with a 95% confidence, but your answer has to be correct to within plus or minus 5. So that is that E value. Okay, so you want to estimate within plus or minus error 5. So plus or minus error 5, that is the E is 5. So you want to get a 95% confidence interval. That's what you're going to use. So the Z table value that goes with 95% confidence interval is 1.96. So the question now, going back to that sigma thing, the formula, you need the sigma. But if you read the question, is that given any kind of hint about the sigma? So what is that? According to this, this one cup of coffee contain an average of 115 milligrams of caffeine. So that is the average. The average has nothing to do with the sigma though. Okay, so that average is the x bar or the mu. That has nothing to do with the sigma. So this value will not give you any information about the sigma. So that means kind of you are stuck unless there's any other hint about the sigma. So in this question there is a hint actually. So that hint is this part. So it says that with amount per cup ranging from 60 to 180 milligrams. So it says that the range is going to be 60 to 180. Okay. So you remember that, like if you assume sort of the mount shape curve for the caffeine content. So if you assume that, you already know something about the range. So you know that if it is a mount shape, within plus or minus 3 standard deviations, everything is there. So if you are, like in the very beginning we did that, if you are so looking at a sort of a mount shape curve, the very empirical rule, within plus or minus 3, the whole curve is there approximately speaking. Okay, so in other words, so within plus or minus 3 standard deviation here, 3 standard deviation, 3 sigma. So pretty much, so the range has to be approximately speaking 6 standard deviation. Okay, 3 sigma. So approximately speaking, so that's the range. If you pull a data set out, the range sort of, that has to be 6 standard deviation, right? So everything has to be within 3 standard deviations of the mean. But the thing is that now, but you remember that at the same time, we look at 95% of the curve within 2 standard deviations of the mean. Okay, within 2 standard deviation, 95. So in other words, actually either you can use this or this. If you use this, you are looking at the 95% range though. Okay, but this is the right one to use rather than this one. Because the reason, there are kind of 2 reasons actually. If you pull a sample out of that, later on you're going to pull a sample out of that. Okay, and the thing is that you're not going to get the values, these extreme values, right? So the chance is very little. Okay, so the other way around, so this gives you the range divided by 4, in other words. Okay, so the sigma is approximately speaking range divided by 4. So what happens is that if you use this formula, you are dividing by 6. So in this case, you are dividing by 4. So if you divide by 4, you are going to get a bigger value here. If you divide by 6, you are going to get a smaller value here. By putting a smaller value here, okay, you're going to underestimate that. So because you do not know anything about that sigma, so you want to make a conservative estimate, okay, for sigma. You want to make a conservative estimate. So in other words, if you put a 20, eventually you might be looking at something less. You might not achieve your goal. You have a goal to achieve. So you want to have a conservative estimate, so you don't want to divide by 6. Okay. So here, this way, you might be, your sample size might be little bigger than what you want, but you are safe. Okay. So that's the reason you do that way. So this is the right one. The range, the standard deviation is a range divided by 4. We are doing this thing because nothing is given in here about the sigma. But if there's something is given here about the sigma, if they say that the sigma is approximately something like 25 or something, you use that 25. Okay. But here nothing is given about it. So that's why we are doing this. So it's 30. So use that 30 right in there. So you evaluate that. So that is going to be 138.29. You remember I said that you don't round it down. Usually this is an integer. So usually you round it down. You take 138 because this is even less than 0.5. Okay. But even if it is less than 0.5, with any fraction, rather than rounding it down, you round it up. Okay. Unless you get the whole integer. So here there's 139. So the sample size required is 139. So by again going back here, this 139 might be little bigger than what really you want. But so you will achieve your goal. Okay. So alright, so this is how you estimate the sample size required to estimate the population mean mu. So in other words, we do this thing, we figure out this before you pull the sample. Then once you figure out that, then you go ahead and pull that big sample. Okay. And also you remember that, so when you pull a 139, this big sample, you really don't need that thing as long as these values are continuous. That's a pretty big sample. So that this part will taken care of actually. Alright. Because this is already big. But suppose here you ended up with a very small number like a 15, 16, something like that. So in that case, this better be normal. Okay. So that's the difference. Alright. So that's about this one. Okay. The estimating the sample size required to estimate mu.